speak your lost and
I'm glad to see you all here. More than I expected. Wow. I'm Nick Craigwood, and I'm going to talk about deadlocks today. If you've done any concurrency work, you'll find a deadlock sooner or later. So this is an intermediate level talk. So I'm assuming you know what a Go routine is, and you have some idea of what a channel is and what a mutex is. And we'll go over the use of those in a bit. And those deadly ingredients make a deadlock. I put a link to the code samples at the bottom there if you want to follow them during the talk, but you don't need to. They'll be on the screen. They may be a bit small for the people at the back, but let's hope not. So in this talk, we're going to learn what a deadlock is. We're going to learn how to debug them and how to avoid them in future. It'll have lots of real-world examples, culled from dozens of painful examples in the rclone code base. I learned about deadlocks the hard way, by having to debug lots of them. And I'm aiming for this to be the kind of talk I would have liked to have listened to when I knew nothing at all. Hopefully everyone, no matter how experienced, will pick up a few tips. But first, a little bit about me. At the moment, I'm mostly doing open source coding on rclone, with a bit of consultancy. I've been using Go for 9 years, actually, I think it's 10 years, since before version 1. I got into it when I was a busy CTO and found I was doing nearly 100% people management, and I decided I needed a little bit of light relief in my spare time. So I learned Go, because it sounded interesting and cool, and after writing a few small things in Go, I then started the rclone project in 2012, and it's been growing ever since. Now with 30,000 stars on GitHub and millions of downloads a month. That's been quite a ride, but I'll save that story for another talk. Since all the real-world examples in this talk come from rclone, I'll tell you a little bit about it. rclone is a highly concurrent command line tool to sync your data to and from any cloud storage system. It supports over 40 providers, including S3, Dropbox, Google Drive, Azure, and loads more. It tries to do everything it can to minimize your network and disk bandwidth, and to minimize the chance of data corruption. It can also mount your cloud storage system as a network drive using its Fuse filing system. To make it run fast, rclone is riddled with Go routines, and the inevitable channels and locks which go with them. And in turn, the inevitable deadlocks. Before I started on the rclone journey, I knew nothing about deadlocks. So, what is a deadlock? Here's Wikipedia's rather abstract definition, which I don't like very much. Something to do with one process holding something another process needs. I prefer to think of deadlocks as a catch-22 situation. Rather like a newly graduated developer, you need experience to get a job, but you can't get experience until you get a job. In a deadlock, the other process has something you want, and you have something the other process wants. And you are both prepared to sit there and block forever until the other process gives you what you need. I'm sure we've all been in situations like that. So let's go through a deadlock in diagram form. Here we have two Go routines, the blue circles, labeled process 1 and process 2, and two locks, the pink squares. Each lock could be a sync.Mutex, or a read-write mutex, or maybe even a write to a channel. The exact mechanism for deadlocks isn't important. The first step is process 1 takes lock 1. All good so far. The next step is process 2 takes lock 2. Again, all good, nothing to see here. Now process 1 attempts to take lock 2. This causes process 1 to block and wait for lock 2 to be released, as lock 2 is already held by process 2. We haven't reached deadlock yet, as everything could be resolved as soon as process 2 drops lock number 2. However, it doesn't do that. Process 2 now tries to take lock 1. This is unsuccessful because lock 1 is taken by process 1, so process 2 blocks, waiting for it to be released. Now process 1 and process 2 are blocked. They will never proceed, as each one is waiting for the other to release a lock. These two processes are now deadlocked. This means that some part of your program has stopped working, and it will never work again. So let's go through that in Go form this time. Here we have a simple process. Sorry, here we have process 1 and process 2, just like in the previous example. And they're going to sit there in a loop, taking and releasing lock 1 and lock 2. The only difference between process 1 and process 2 is that they take and release the locks in different order. This code looks like it should work. Why not? It's just taking a few locks and releasing them, but it will deadlock pretty soon. And this is what happens if you run it. The first thing to notice is that the Go runtime has detected the deadlock, giving the nice friendly message, all Go routines are asleep, deadlock. The runtime gives a backtrace, or a stack trace, of all the Go routines that are running, which is very useful for working out what went wrong. The disadvantage of this is that they can be very long. Even this tiny example needed 2 slides to fit it on. So looking at the slide, Go routine 1 is waiting on the select with no cases that we put in to stop the program ending too soon. We can ignore that. Go routine 17 is in state sem-acquire. It's deadlocked, calling the sync.Mutex implementation. You can see 2 lines of backtrace for the sync.Mutex implementation, and then on the 3rd line you can see our code. Here's the next bit of the output. In Go routine 19, you can again see a different bit of our code. It's also calling the sync.Mutex implementation. Again, it's deadlocked in the sem-acquire state. You'll be hearing a lot about the sem-acquire state. So I put arrows in the bits of code that the backtrace indicates the Go routines are executing. You can see that process 1 has taken lock 1 and is block taking lock 2, whereas process 2 has taken lock 2 and is block taking lock 1. This is a clear deadlock. Whenever you see a trace where a single Go routine takes more than 1 lock, you should be thinking about deadlocks. And this is exactly what we expected for our initial diagram. Process 1 is block taking lock 2, and process 2 is block taking lock 1. See the nice crossing over of lock lines. It's nice to see theory and practice agreeing for once. So you'll have noticed that Go can detect deadlocks. That is very useful. But unfortunately, it very rarely detects deadlocks in actual code. A major disappointment. This is because all the Go routines in your entire program have to be asleep for it to trigger. And in my experience, that almost never happens, except in toy examples like these. There's always something else going on, like log collection or statistics calculations or something like that, which means the race detector doesn't fire. So here's the code again. We've added 1 extra Go routine, as indicated, which just does a sleep for a minute. And if we add that, the deadlock detector does not kick in, and the program deadlocks silently. Or other part of the program, process 1 and process 2 is deadlocked, but the rest of it's working fine. Unfortunately, this is the usual state of affairs when debugging deadlocks. Some part of your code just stops working, with no other symptoms. Enough of your code may be working to give you the idea that it isn't broken, but some important part isn't progressing. We'll see in the next section of the talk what to do at this point. So here's a quick diversion. As I expect this question has popped into your mind already. Can we use channels instead of those nasty mutexes to avoid deadlocks? Alas, no. You can cause a deadlock with channels just as easily as you can with mutexes, and we see an example of that later. In my experience with rclone, only about 10% of the deadlocks are with channels, so they are certainly less likely. So why do we get deadlocks? There are 2 ingredients. The first is concurrency. Without concurrency, that is, things happening at the same time, we can't have deadlocks. This means that the single-threaded code can't have deadlocks, which is the point we'll come back to. The next magic ingredient for deadlocks is locking. And when I say locking here, I'm including channels, reading and writing to Sorry. Reading and writing to channels can block your program just as easily as mutex is. And if I wanted to be really precise, I'd say shared resource acquisition instead of locking, because you can get deadlocks on other things other than mutexes and channels, for example, using file system locks. So where do these locks come from? My excuse is the race detector made me do it. So what do we do to pacify the race detector? We put locking in. And sooner or later, once you put enough locking in, you will cause a deadlock. I'm joking here, of course. The Go race detector is wonderful. It tells us about data races which would have caused silent corruption in our programs. I'm just going to sing the virtues of the race detector, and if you're not using it, start using it. It's a technological marvel, and it seems to me very close to magic. The race detector will tell you when your program runs a risk of memory corruption due to unsafe accesses. If you're writing concurrent programs, you should run your tests with the race detector, and if you can, some of your production binaries too. Any problems it finds are always real problems. I've never known it made a mistake. However, when fixing the things the race detector points out, do think about what deadlocks you're about to create. In particular, think about what locks might be already held and what locks you might want to take in this Go routine. Here's an example I'm going to use quite a few times. Hopefully that is legible at the back. It's a simplified example from our clone's Fuse-based filing system for mounting remote cloud storage as if it were a local disk. On the left, you can see the definition of the file struct. It has a name, size, and parent directory. It has a path method, which returns the full path of the file. And it needs to ask its parent directory for its path in order to do that. It has a size method to return its size, and a truncate method, showing how the size of the file might get mutated. On the right, we see the definition of the directory struct. This has a name, parent directory, a slice of files it contains, and a slice of directories. It has a path method for returning its full path, and it needs to find out the path of its parent here too. It also has a size method, which adds up the size of the files in the directory. There's no locking in the code above, but a few runs with the race detector reveals that locking is needed. Excuse me a moment. So to prevent those nasty data races, we add a sync.Mutex called mu into the file structure. The name lowercase mu is traditional in Go code. If you look through the standard library, you'll see it everywhere. Then in each of the methods, we lock the mutex with mu.lock and defer the unlock of the mutex with the defer mu.unlock. This means that none of the methods will ever run concurrently, and it means our instant variables are safe from data corruption, data race corruption. Hooray! This is a standard pattern used in Go concurrent programming, and hopefully you've seen it before. Take the lock at the start of each method and defer its release to the end. What could possibly go wrong? So we do the same thing in the directory structure. Add a sync.Mutex called mu to the struct, and then call mu.lock and mu.unlock. However, we're unwittingly caused a potential deadlock by doing this. I say potential deadlock here, because when you run this code, it will quite likely work just fine until the right conditions are met, usually being put into production. Most deadlocks are like this. They don't stop your code the first time you create them. They come back to bite you later when you're least expecting them. Here's a bit of code to exercise the directory and file abstractions, which will provoke the deadlock. Process 1 just calls file path in a loop continuously. Not exactly normal usage, but we're trying to provoke the deadlock here. Process 2 just calls directory size in a loop continuously. In our main function, we create a root directory and put a file into it, then start Go routines to call process 1 and process 2. We also start a race detector defeating Go routine, which just sleeps for a minute. And finally, the empty select statement to sleep the main Go routine forever. Remember, if we exit the main Go routine, then our program will stop, and we don't want that. So we run the program, and it's now sitting there doing a whole heap of nothing while deadlocked. So how can we find out what it's doing? If you're running a Unix-based platform, for example Linux or macOS, then you can send the processor sync.Quit, either using the kill commanding or pressing Control \. This will produce a nice backtrace. Windows platform users will have to work a little harder and install the HTTP debug handler from net http-prof, and I'll show you how to do that a bit later. This is what happened when I sent the file and directory example program the quit signal. I got this nice backtrace. It's quite long, but there's a lot of stuff we can ignore. The output's divided into stanzas, and at the start of each one, a little description. Here it says, go routine 0, idle. Following that is a reference to a line of source code, plus the code itself, one for each level of the call stack. In fact, this is the system go routine doing something in the runtime. We can ignore it because it doesn't have any of our code in the backtrace. Next we see go routine 1, select no cases. This is the wait forever select go routine code, go routine, which we put in to stop the main function exiting. We can ignore this too. Finally, we start to see some of our code. We see go routine 5, sem-acquire. This one's important. Sem-acquire means it is blocked when trying to acquire a lock. Blocks means it's sleeping. For most deadlocks, you are searching for these sem-acquire lines first. Below the sem-acquire, you can see a couple of lines of code in the runtime. These are in the sync.Mutex code, and finally a bit of our code in dir.path. We can see that dir.path was called by file.path, so by the time the go routine tries to acquire the directory lock, it has already acquired the file lock. Next in the backtrace, we see go routine 6, also blocked on sem-acquire. It looks quite similar to the last one. 2 lines in the sync.Mutex code, and then it trying to acquire the mutex in file.size. Looking up the backtrace, you can see that file.size was called from dir.size, which means that this go routine acquired the dir lock first, and is now blocked on acquiring the file lock. If you have an editor, if you have an editor that lets you click on these file names, it's really helpful to jump around the code at this point, so you can see exactly which mutexes are taken and exactly which bit of code has been run. Under that, we see go routine 7, sleep, which is our deadlock defeating go routine, which we can ignore. So we've found the 2 important go routines, the 2 important things in the backtrace, the ones with sem-acquire. And finally, on the end, you get a register dump, which you can ignore for this purpose. I'm sure it's useful for low-level debugging, maybe if you're writing assembler, but I've never needed it for deadlocks. Here I've annotated the code from the backtrace, showing where each go routine is blocked. The fact that both parts of the code are blocked on acquiring a mutex are very suggestive that there's a deadlock. Let's look at dir.path on the left-hand side of the screen. We saw from examining the backtrace that this go routine already holds the file lock and is now blocked trying to acquire the directory lock. On the right, file.size is already holding the directory lock, but is blocked trying to acquire the file lock. This means that these 2 functions are deadlocked and will block forever because the locks they're waiting for will never be released. When debugging a deadlock, it's often helpful to try and write out the timeline of the deadlock. And this deadlock occurs whenever the size method on directory is called concurrently with the path method on file. The numbers on the left of the code line show the ordering of the calls to each process. The arrows point from the block locks to the place the lock is held, and them crossing is very suggestive of a deadlock. You might think there's very little opportunity for this to happen, given the short windows of opportunity. Each of these instructions will be over in a few nanoseconds, won't it? However, if the deadlock is possible, it'll happen sooner or later. One thing to bear in mind is that locking instructions are particularly slow. They use slow memory-locked instructions or scheduled go routines or processes, which often turns something you thought would never happen into something which always happens. I'll just quickly loop back to how to install the HTTP debug handler, which you can use to collect backtraces when running Windows. Look up the docs for net HTTP pprof. Everything you need is in there. You can collect the output with curl, or just look at it in your browser. You can use this on any platform, of course, and you might consider leaving it in your production code when your production code is deadlocked and you want to find out why. It's pretty simple, though. Import net HTTP pprof and then run a little Go routine as an HTTP server. You may have an HTTP server running in your code you can attach this to already. You might also want to think about security as well. The output from the HTTP debug handler is similar to the output from sync.Quit, with one stanza for each Go routine and a trace showing position in file and the actual line of code being executed. It doesn't call out the state of each Go routine in the same way as the sync.Quit output, but it's easy to see that two Go routines here are blocked on semi-acquire mutex, which means blocked on acquiring a mutex, as you might expect. One important difference here is that this output collapses Go routines with identical stacks, which can be very useful if you've got thousands of Go routines. When you're tracking down a deadlock in a real-world program with lots of concurrency, you'll find that the backtraces get very long very quickly. Deadlocks have a nasty tendency to spread through a good fraction of your running Go routines, until they're all waiting on a lock of some kind of like something crystallizing out of a solution. Here's an example of a backtrace a user sent me while debugging an R-clone deadlock. It has nearly 2,000 lines, covering 260 Go routines, and is about par for the course. There are 14 Go routines blocked on acquiring a mutex, 123 blocked in a select statement, 121 blocked on sending or receiving to a channel, 1 in a system call, and 1 idle. So that's one Go routine doing something useful. If that sounds like looking for a needle in a haystack, it is. We need some help here. Luckily, there is a great tool called panic parse, which helps enormously here. It condenses down that 2,000 line log into a nicely coloured 142 line log with one stanza for each different type of Go routine. It shows there are only 14 different types of Go routine here, which makes working out what's going on so much easier. It also has a nice web output, which I haven't tried yet, but I put up a screenshot here from the GitHub page so you can see what it's like. Those clicks to the source look particularly useful. This tool has saved me so much time when debugging deadlocks. So, thank you, Mark Antoine. The text output of panic parse shows a stanza for each Go routine, rather like we've seen before. It aggressively collapses Go routines with similar stacks together, like the HTTP debug handler, but better. Here's what a stanza looks like. On the left, you can see a number, in this case 7. This is how many Go routines like this there were. And it really usefully, it prints the time that it's been paused, in this case 85 minutes. Looking for the first Go routine to pause can often be a big clue. It is then reasonably easy to see that there are only a few Go routines that could possibly be the problem, namely the ones that are waiting on locks that have taken locks already. So it can immediately ignore nearly all the Go routines. I'm not going to lie, it's still tricky working out exactly what's going on here, but it's so much easier with panic parse. So we've talked so far about what a deadlock is and how to find them and debug them. But a better strategy would be to avoid them completely. I'm going to talk through a number of different techniques for avoiding deadlocks. Unfortunately, there isn't just one thing I can say. Do this and you'll never get a deadlock again. Alas. We're going to start with some easy things to fix, then move on to some harder problems. I said there was going to be an example of deadlocks with channels, and here it is. It starts with a job struct. You can see it defined at the top. It has a constructor, new job, which doesn't do a lot in this example. The process method is the important bit. For each job, it runs the job. In this case, it doesn't actually do anything. However, in the process of running the job, more jobs might be created. In this case, it picks a random number as to whether to create more jobs or not. Those jobs are then returned in a slice for further processing. This is simplified from an rclone example, where each job listed a directory, and they returned jobs to list subdirectories. So here is the process jobs function, which takes a wait group and a channel of jobs. While running, it takes a job out of the channel, processes it, and adds any created jobs back into the channel. It's written like this with the channel, so we can run a few copies of process jobs concurrently to increase the throughput. And that's what happens in the main routine. We start 3 copies of the process jobs function to increase the throughput. It's worth explaining what the sync wait group does. We're using it to keep track of the number of active jobs, not the number of active Go routines. Whenever a job is created, the wait group is increased with the add1 method. And whenever a job is finished, it's decreased with the done method. When the wait group goes to 0, we know all the jobs are finished, and we wait for that moment with the wait method right near the end. So that looks like totally reasonable code, but you guessed it. There's a deadlock. We run it for a while, and it creates a job, does them, creates them, jobs them, does them, until deadlock. So let's just go through this trace. The first Go routine shown, Go routine 1, is our sync wait group, waiting for the others to finish. So we can ignore that for the moment. Go routine 6, 7, and 8 are all in state chan send. That is, they're waiting for a channel to be emptied before they can send some data down it. You can see they're all waiting in process jobs. The problem is that somehow all 3 of our Go routines are blocked writing to the channel, and none of them are reading from it. Because those 3 Go routines are the only place we read from the channel, this means that the channel will never get emptied, and those 3 Go routines will never get unblocked, thus creating a deadlock. This is the code with the deadlock positions marked on it. The 3 process jobs functions are all trying to write a new job into the jobs channel. However, none of them is reading from the channel, so none of those writes will ever succeed. A classic deadlock, this time with channels. We can also see that the sync wait group wait method being called to wait for the job processing to be complete. This is now part of the deadlock too, as it will never proceed either. The wait group wait isn't the cause of the deadlock, but it's collateral damage. And this is very common when looking at deadlocks. Often the collateral damage overwhelms the cause of the deadlock, as we saw in the long trace example. And that makes it very hard to work out what's going on. So what's the solution? We need the process jobs function to be either reading from a channel or processing a job. We don't ever want it to be blocked and writing to the channel, because if one Go routine can get blocked, then all of them can. The easiest way of achieving this is by sending into the channel in a new Go routine. The original Go routine is released to receive jobs from the channel, while the new Go routine sends the new jobs to the channel. This has the consequence that there might be an indefinite number of Go routines with a few jobs to add to the jobs channel hanging around. If that's a problem, then a different design is needed. Note we also move the active jobs done call into the new Go routine. We can't signal a job is finished until all of its job children are safely queued. If we do that, then the main function will end too early. Yeah, guess what my first iteration of this code did. Anyway. So the moral of this channel deadlock is simple. Don't send and receive to the same channel in the same Go routine. It's a recipe for deadlocks. As I said earlier, this example came straight from rclone. This deadlock took some time to appear. It took a particular user with a particular workload, and it took me a few iterations to find a solution, which didn't deadlock or end too early. concurrency is hard. Here's an example with read-write locks. Here we have two main functions, RO and RW. RO takes a read lock, and then calls more RO, which in turn takes the read lock again. This is allowed. Read locks can be taken multiple times. The read-write function takes the lock for write. This looks harmless, and it works most of the time, until suddenly it doesn't, and you made a deadlock, as we'll see in a moment. This example was also simplified from a real-world example from our clone, which was caused by a bit of careless refactoring. The first step of the deadlock is the read lock being taken in Go routine 1. So far, so good. The next step is the read-write lock being taken in Go routine 2. If you read the docs, you'll see a read-write lock prevents any new read locks happening, so that the lock eventually becomes available. There's also a note about recursive locking not being allowed if you read carefully enough, which is exactly what this example is about. The deadlock happens when Go routine 1 attempts to take the read lock again. This is called recursive locking, and none of the standard library locking routines support recursive locking. This lock is blocked because the read-write lock in Go routine 2 is in the process of being taken. This means that the more RO function will never return, and the RO function will never release its lock. So in turn, the RW function will never acquire the mutex, thus a deadlock. And the moral of this story is don't take a read lock twice in the same Go routine. It might sound completely obvious, but it's really easy to do by accident. It does warn explicitly against doing this in the docs too, but of course I didn't notice that until after I caused this deadlock. I could show a commit message for every one of the examples in this talk, but since we haven't got all day, I'll just put this one up so you can feel my pain. I always find debugging deadlocks hard, even with all these nice tools. So when you have to debug one yourself, just remember that. Objects which contain locks that call each other's methods are a deadlock waiting to happen. This happens naturally in more complicated systems, for example, file systems. And great care is needs to be taken not to cause deadlocks. Going back to the directory and file example, the problem is caused by the fact that the directory and file both call each other's methods. The general solution to this is called total lock ordering, but we're going to look at some easier mitigations first. Here's one example fix for the deadlock. I call this technique shortening the locking window. What we've done here is release the mutex in file.path as soon as we can. And in doing that, the lock and unlock of the file and directory mutexes no longer overlap. At the top, you can see the original function. Below that, you can see we've modified it to make a temporary copy of name and parent from the file structure, and then unlock the mutex. This is enough to fix the deadlock, as shown before. It does introduce the idea that the path function might return an out-of-date path if the name or parent changes during the call of path. Some thought is required here as to whether this is okay or not. So in order to minimize the chance of deadlocks, release locks as soon as possible to shorten the locking window. Specifically, release them before calling any other functions or methods which might take locks. I've even resorted to using the defer statement to defer calls to get them outside the locking of the current method. Another easy mitigation is to notice which members of your object are read-only. These should be assigned to once in the initialization of the object and never written again. These don't need any kind of locking. Concurrent reads are always safe. So for example, here we say that the name of files and their parent directories never change. I've moved them above the mutex definition to give the idea that they aren't and don't need to be protected by the mutex. In this rename-free world, we don't need any locking in the path method at all. And we fix the deadlock by having no locks. Best kind of locking, no locks. So if you can identify variables which are read-only, you don't need locking for them, and they can be accessed outside the lock. No locking means no deadlocks. Here's a sketch of some other things you can do, which I didn't have room to make examples for. One way to reduce deadlock possibilities is to split the lock into multiple locks. So use more fine-grained locking. This makes it less likely that the locks will overlap. Or maybe you can use atomic for some accesses. Perhaps you're incrementing a counter or something like that. Atomics never block your process, so can't cause a deadlock. They come with their own caveats, so use with care. Using a read-write mutex is a great help for reducing lock contention, provided you've got methods which only do read things. Allowing many read-only methods to run at once stops them blocking and minimizes the chance of deadlock. And if you're using channels, buffer channels help avoid deadlocks too. Because they don't synchronize to go routines. Deadlocks can still occur when the channels get full though, so it won't cure everything. Now it's time to bring out the big guns. Total lock ordering. The ultimate solution to this is to impose total lock ordering. This means that you assure that if the locks overlap, then you always take one lock first. So if you have two locks, A and B, you always take lock A before taking lock B in the same go routine. This makes sure we never have a deadlock. I'm sorry to say though, it's much easier to say this than do it in a structured program with locks inside objects. In practice, with object-based locks and methods, this means making one object superordinate and another subordinate. For example, this might mean that the directory can call file methods with a directory lock held, but the file methods mustn't call directory methods with the file lock held. In a perfect world, we'd be able to specify what we want to a linter. I don't think such a linter exists yet. If it does, do tell. In the meantime, comments like this one from our clone are what we have to live with. It explains to the reader that the cache and item objects are tightly linked. And if you don't want to cause a deadlock, then don't call cache methods from item with the item lock held. This means that when you change code, you need to be very careful to uphold these invariants. If you don't, deadlocks will ensue. So write lots of comments and do lots of code reviews when writing this sort of code. Debugging deadlocks can get very hard, very quickly. And I used to think I was pretty good at this computer science stuff, but debugging deadlocks frequently makes me feel very stupid. So if the locking gets too complicated, then you can bail out and use a single-threaded engine to remove all the locking. Single-threaded likely means lower performance, but maybe having no deadlocks is worth it. You'd communicate with the engine over channels in a request-response style. Typically, you'd send the channel for the response over the request channel. This makes things much simpler, and it's very much in the classic Go style. But making everything single-threaded will drop your performance, which may be unacceptable. But just do remember this when your brain's melting. Single-threaded, oh yeah. So you'll notice there's been a lot of struggle with deadlocks in the previous slides. And it would be nice if there were tools to help us find the deadlocks before they happen. Well, there are a number of notable tools for finding deadlocks in Go code. Dingo Hunter is based on a theoretical approach for finding channel-based deadlocks. You may have caught the talk about it here in 2016. It only works for unbuffered channels, alas, which limits its scope. Go Deadlocks is a practical tool for finding violations of total lock ordering, and has been used to find deadlocks in CockroachDB, for example. I've used it on the rclone codebase a few times. It comes up with error messages that look rather like those from the race detector. But unlike the race detector, it detects potential deadlocks before they happen. So you can run this in your code which hasn't deadlocked yet. Go Deadlock only works for Mutex deadlocks, not channel deadlocks. But as I said before, this is probably 90% of the deadlocks I see, so it's an excellent start. Go Deadlock's very easy to use. Here's the example from its GitHub page. You just replace your sync imports with a Go Deadlock import, and when you run your code, it will give total lock ordering errors. So I ran it on our file and directory example, and this is the output I got from Go Deadlock. It nicely points out the potential deadlock. The top half is the first Go routine, and what it's saying is the directory lock, and then the file lock was taken. But in the bottom half, in the other Go routine, it says the file lock was taken first, then the directory lock. It isn't saying a lock happens, it's just saying one could happen. As it says at the top, potential deadlock, inconsistent locking. Saw this ordering in one Go routine. I've used Go routine on more complicated examples, and I have to say I found the output quite difficult to interpret. This is because deadlocks are hard to understand, rather than a shortcoming of the tool. So if you do plug Go Deadlock into your massive concurrent program, expect a bit of head scratching while you work out what the error messages mean. When I want to use Go Deadlock with rclone, I run this little script. It searches and replaces all the sync.Mutex and sync.Mutex with their deadlock detector versions. Unfortunately, I find you can't leave Go Deadlock in production code, as it has too much a performance impact. I'd like to have a neater way of enabling it for testing, but I haven't figured that out yet. This has been quite an intense talk. I'm sorry about that. And we've gone over a lot of concurrency-related things, but I hope you all now have some idea of what a deadlock is, how to debug deadlocks, and how to avoid them in the future. Deadlocks are the curse of concurrent programming. However, there are good tools for finding them and debugging them, and there are some promising tools for helping prevent them happening in any code base. So, if, or rather when you get to debug your first deadlock, just remember, don't panic. Or rather, do panic and collect a backtrace. That's the end of my talk. Thank you all for listening. Now I think we got some time for some questions. Do we have a? So any questions? We have a man with the mic.
Hi. Thanks for the talk. Just quickly, before I ask my question, we use Go Deadlock, and we created a package that wraps it and uses a build tag to either enable it or just pass through the regular sync.Mutexes.
Oh, perfect. Thank you.
But my question was, have you considered the use of formal specifications to try and detect deadlocks before you have to run into them?
That is a good question, and the answer is no, I'm not that. I'm much more of a sort of practical developer fixes problems when they come across them. But yeah, I think there's an opportunity for more tools, definitely. And I think there's opportunity for static analysis. I think there's opportunity for linters, finding deadlocks. So yeah, I'd like to see more work in that space. But yeah, that's not me, alas.
Hi, thanks for the talk. I was just having a question I was curious about is, how do you unit test deadlock, or condition? Because thread.sleep or, sorry, I don't have any idea. I haven't unit tested I've unit tested things like a go routine or a channel or mutex, but is there any way to prove it, without, from before we get to the deadlock? It's very similar to what he said, but via unit tests.
Yes, well, I think if you were to have unit tests which use the Go Deadlock package and then paid attention to any messages it produced, I think that would go a long way towards not having deadlocks in production. But it's quite a steep learning curve plugging Go Deadlock into your program. So be prepared for lots of puzzling and thinking, what does this mean? What's it trying to tell me? So, but yes, I think it's definite possibility. Unit testing with Go Deadlock.
Cool. Thank you.
Any more questions? No more? Okay, we'll wrap it up there then. Thank you all for coming.